So in this video, we are going to exploit this idea of using Venn diagrams to the maximum. Okay, so we are going to be able to define two very important concepts, which are the null space of a matrix or null space of a transformation and the range of a matrix or range of a transformation. So let's consider the most general case. So a matrix that has m rows and n columns, and this is a linear transformation, yeah? So this linear transformation is acting on vector x and the output is vector v. So what is the dimension of vector x? X has to be n dimensional, yeah? Because it must have the same number of elements as there are columns in the matrix. While the output vector v is m dimensional, yeah? Because the size of vector v is equal to the number of rows in the matrix. Therefore, this transformation, which is a general one, is transforming a vector space that is n dimensional. So let me draw it like this. So we have an input space which is n dimensional, and it's converting it into an output space which is m dimensional. Now, can we say that the entire n-dimensional space is mapped into the entire n-dimensional space? Maybe it is, but maybe it isn't. So there are some cases, remember when we were looking at the projection, this example of a transformation which projects every vector into the x-axis, yes? So when this happened, the entire input space, which is on the left here, is going into a subspace on the output space. So all of the possible vectors in the two-dimensional space are going into the x-axis for this example. So sometimes this happens that all of the input space is going into a subspace of the output space. Yeah. So we can draw that in our general case. So in a general case, we can say that all of the input space is going into a single subspace of the output. Yeah. So remember, this is applying matrix A. And this subspace of the output is what we call the range. Okay, so that's what the range is. Now, at the same time that all of the input space can go to a subspace in the output, we saw recently, also in this case, in this example of a transformation that is projecting every vector into the x-axis, we saw that sometimes when the determinant of a matrix is 0, there is an infinite amount of vectors in the input which go to a single vector in the output. Yeah. Although here in this previous video I was lying a little bit. I was lying, it's not a serious lie, but I was calling this green circle in the input, I was calling it a vector space. But it was not really a vector space because it doesn't include vector 0. And remember, one of the axioms for a vector space is that it must include the vector 0. Yes? So this line, which corresponded to this line here, yeah, is not a subspace. However, this other line, in this case the y-axis, this line is a subspace because it includes vector 0 inside it. Yeah. And where do vectors in this line end? So when you start with a vector in the y-axis, for example this one, and you project, so you apply this transformation of projection into the x-axis, you end up in vector 0. So actually any starting vector inside this line will end up in vector 0. So now we could draw, this time, yes, this is a subspace which includes vector 0 and which is all mapped into vector 0. Okay, and this is now a subspace. Yeah. So let's include this in our Venn diagram for the general case. So to include this, I'm going to draw a subspace of the input, which includes vector 0. And all this subspace is mapped into a single point, which is vector 0 in the output. Okay? Now, this subspace in the input is called the null space. And this completes our intuitive explanation of what the null space is and what the range is. Okay? We are going to say very interesting things about the dimensions of the null space, the dimensions of the range, and how they are related to the dimensions of the input and the output space. So these are very, very beautiful results. But first, let me state mathematically with symbols and equations what the range and the null space is, rather than drawing this Venn diagram. Okay? So the range is the subspace of the output into which all of the vectors in the input are mapped. So how can we mathematically write this subspace? So we could say that the range is the subspace given by A times X for every possible vector X, right? So we are applying the transformation A to an input vector X. So if we consider every possible input vector X, then A times X is the range. So how could we write it? Actually, notice that A is a matrix that has m rows and n columns. Yeah. So let's write the n columns here: C1, C2, up to Cn. And then vector X is our input vector that has n elements, n components. Yeah. And these components can take any value because we want to find all possible input vectors. Yeah. But this A times X, actually, if you do matrix vector multiplication, this ends up being a linear combination of the columns given by this. It's x1 times the column C1 plus x2 times the column C2 all the way up to xn times the column Cn. Yeah, so it is a linear combination of the columns. But now we just said that we want to consider all possible input vectors X, all of the possible input vectors, right? So we are considering the entire input space here, all possible input vectors. Therefore, the coordinates x1, x2, up to xn can take any value. And this should ring a bell. So when you are considering all of the possible linear combinations of a set of columns for any coefficients, this is called the span of the set of vectors, right? This was the definition of span. Therefore, the range is the span. So let me write it. Range of A equals the span of the n columns of the matrix. And this is the formal definition of the range. And this is how books will define the range. Yeah? This is also the reason why the range is also called the column space, which is a easier to remember name. Next, let's define formally the null space of A. So remember, the null space is all of the possible vectors in the input that get all mapped to a point 0. Yes? So the null space is equal to all possible solutions of the system or all possible solutions to the equation A times X equals 0. Okay? So you solve this system, you solve it for X. And you will get that the solutions for X in general is either a single number equal to 0, which is the trivial solution, or it is an entire subspace. For example, it's a line or a plane or whatever. Yeah? And that set of solutions is the null space of the transformation A. Okay? So, thanks for watching.